I've been on a mission since buying my first home a couple of years ago to automate everything. But in the last few weeks, I've come up against my biggest challenge yet, my fireplace. This is a Carlton & Jenricks i1800 range electric fireplace. It has a plethora of options available to it, like adjusting LEDs for the flame effect, the sound, and of course the heating options. From some initial research, the fireplace does have an app you can use to control it, as well as integration with Alexa, but I couldn't find any way to integrate it into my Homeassistant setup, as that's my ultimate goal. But there is another way. In this video, I'm going to show you how I reverse engineered the sub-GHz radio signal from this fireplace remote control and built an ESP32 powered radio module using the CC1101 and MQTT to integrate all the buttons with Homeassistant. Let's get started. Before we go any further, let's take a step back and answer an important question. What exactly is a sub-GHz remote? Most of us are familiar with traditional TV remotes, the kind that use infrared light to send commands. In fact, in one of my very first videos on this channel, I built an ESP32 device that sends and receives infrared signals. Infrared is incredibly common, mostly because it's cheap, simple, and well understood. But it also comes with some pretty serious limitations. Infrared remotes work by flashing patterns of invisible light at a receiver. That means they require line of sight, they have a very short operating range, they can be affected by sunlight or bright lamps, and of course they only work in one direction. So what makes a sub-GHz remote different? Well, sub-GHz remotes don't use light at all. Instead, they transmit radio waves at frequencies below 1 GHz, most commonly around 315 MHz up to and around 915 MHz, depending on region. These frequencies are much lower than Wi-Fi or Bluetooth, and that gives us some advantages. Because of their longer wavelengths, they travel much further, penetrate walls and furniture, use much less power, and are generally more reliable in noisy environments. Another important difference is that sub-GHz remotes can support two-way communication. Some devices simply send a command and hope for the best, like turn on or turn off. Others send a command and wait for a response, confirming that the device actually received it. This is more secure and of course more reliable, but also much harder to reverse engineer. And at this point, we don't know yet which category this fireplace falls into. And of course, unlike infrared, sub-GHz signals aren't standardized, can use many different modulations like ASK and FSK, may include rolling codes or checksums. They can often look like noise until you know what you're looking for. And of course, in some instances, they can transmit too fast for some devices to record. Which means tools that work great for infrared don't always work well here. And that brings me to my first big problem. Naturally, of course, my first instinct was to reach for a tool that claims it can do it all, the Flipper Zero. And this is where things started to go wrong. Now, some of you might already be familiar with this. The Flipper Zero is a pocket-sized multi-tool for hackers and makers. It's designed to interact with the digital world around you, things like RFID cards, NFC tags, infrared remotes, Bluetooth low-energy devices, and some simple radio protocols. Think of it as a modern open-source Swiss Army knife for exploring how everyday wireless systems work. It can read, store, and emulate different types of access keys, and for our purposes, analyze signals, or at least that's what I'd hoped for. But no matter what I tried, from different modulations and frequency settings in the Flipper itself, I couldn't for the life of me get the Flipper to accurately record and replay the signal back from the fireplace, at least initially. So this led me down a rabbit hole of scouring the web for related documentation of the controller itself, its firmware. For instance, the accompanying fireplace instruction specifically references the remote using ASK, modulation. Spoiler alert, it does not. But of course, with every challenge comes an opportunity to learn. So at this point, I put aside the Flipper for something a bit more powerful. So where do we even begin to try and understand how to decode a signal from this remote, let alone clone and replay it? There's two things that are going to drastically help us along in our investigation. The first is URH, or Universal Radio Hacker software, and an SDR, a software-defined radio. A cheap SDR will also work in most situations, but in my case I have HackRF1, which also supports transmitting or replaying the captured signal back. But before we can even use these tools at hand, we need to find out what frequency we're transmitting on, and ideally what modulation the remote is using also. Using URH, we can navigate to File, Capture Signal, select our device and identifier, set the gain to max, or close to max as you can. This is because weak signals in the range of 315 to 433 MHz remotes, sensors, or ASK or OOK transmissions may barely rise above the noise unless we increase the gain. Then hit start. And what we'll see is our button presses coming through as I spam the on-off button coming from the remote. After saving that, we can navigate to the Analysis tab, and this is where the real fun begins. Instead of treating the entire capture as one big blob, the first thing I'm going to do is split this recording into separate signal segments, each one representing a different button press from the remote. This lets URH analyze them independently, which is important, because even buttons that look similar on the outside can behave very differently on the air. With those segments created, I'll let URH auto-detect the signal parameters. This includes things like the modulation type, the symbol rate, pulse timings, and how the data itself is structured. Under the hood, URH is essentially making educated guesses based on the waveform, and in many cases, it gets surprisingly close. Take this remote for example. All our documentation says it's ASK, but even URH thinks it's FSK, solely based on the waveform. Next, I'll switch the view from raw waveform to the demodulated signal. This step is crucial because up until now we're just looking at voltage over time, which I'm sure is great if you're an actual RF engineer, but not very useful if you want to understand what's actually being transmitted. Once demodulated, the signal starts to resolve into discrete symbols, ones and zeros, which brings us much closer to something we can analyze. From there, I'll change the data view into hexadecimal. Personally, I just find hex much more compact and readable than raw bits, and it makes patterns jump out almost immediately. This is where you can often start spotting things like fixed headers, counters, or repeated fields across different button presses. Now let's move over to the Analysis tab. Here, URH attempts to infer a protocol from each of the signal segments, essentially asking the question, do these signals follow the same structure? And if so, how do they differ? By comparing all three, we can see which parts stay constant and which parts change. That difference is usually the actual command like power on, power off, or mode change. This is essential for more complex captures which might have a checksum or use a rolling code protocol to help you spot it if it is. Even if URH doesn't fully understand the protocol, this comparison alone is incredibly valuable. At this point, I just want to do a quick demonstration of a replay attack. What I'm doing here is taking one of those captured RF transmissions and transmitting it back out unchanged. There's no decoding, no modification, just a straight replay of the original radio signal. And as you can see, the fireplace responds exactly as if I pressed the original remote. This tells us something very important. There's no rolling code or cryptographic challenge here. The signal is a static and replayable transmission. Finally, I'll jump over to the generator tab. This is where URH really earns its name. By selecting one of the analyzed signal segments, I can view the underlying data and then generate a brand new transmission based on it. And in this case, that means exporting the signal as a .sub file, a format that the Flipper 0 itself understands. So even though the Flipper couldn't reliably capture the signal on its own, I can now manually generate a valid sub-GHz file for it using URH. And just like that, we've gone from a mysterious waveform to a portable, replayable command. Or so I thought, because even after generating a custom .sub file and loading it onto the Flipper, it still didn't work. At this point, I was honestly pretty frustrated. On paper, everything looked correct, the signal structure matched, the data matched, but the fireplace just refused to respond. So instead of guessing any further, I did what you should always do when you hit a wall like this. I asked for help. I made a post to the Flipper 0 community on Reddit explaining what I'd done so far, shared my pictures and captures, and asked if anyone could spot what I was missing. I want to give a huge shout out to Cthulhu Chan, who went above and beyond helping me debug this, and almost immediately he noticed something important. When we compare a capture from the original remote to the one transmitted by the Flipper, the timing was way off. The original remote was transmitting at roughly 100 symbols per second, while the Flipper was closer to 200 symbols per second. That's a massive difference. And while I'm going to come back to timing later, there was another red flag hiding in plain sight, and that was the frequency deviation. If you're not familiar with it, deviation is how far the signal shifts above and below the center frequency when transmitting data. In simple terms, it's how wide the signal swings when representing a 0 versus a 1. The problem is that the Flipper.sub file uses predefined radio presets, and we strongly suspected that the preset I was using didn't match what the fireplace was expecting. So instead of guessing, we decided to measure. First, I captured the signal directly from the original remote. When I zoomed in on the frequency domain, we could clearly see two peaks, a low peak at 433.904 MHz and a high peak at 433.944 MHz. Now, doing the exact same thing for the flipper's transmitted signal, the peaks were very different. Low peak was around 433.879 MHz, while the high peak was around 433.963 MHz. To get the deviation from a signal like this, all we have to do is subtract those values and divide by 2. For the original remote, that gives us a deviation of about 20 kHz, whereas for the flipper, the deviation comes out at roughly 42 kHz. That's more than double what the fireplace remote uses. And right there, that explains a lot. Even though the data itself was correct, the signal was swinging far wider than the fireplace receiver was designed to tolerate. For the fireplace, this wasn't a valid command, it was just noise. So at this point we know two things. The timing is wrong, and the frequency deviation is wrong. Fixing that means we can't rely on generic presets anymore. Which brings us to our next step, building a custom radio preset from scratch, where we control the timings, the deviation, and every other parameter ourselves. And that's exactly what we're going to do now. At this point, we know why the signal isn't working, but we still need a way to actually fix it. Thankfully, the flipper gives us exactly the tools we need. Inside the flipper documentation, there's support for custom sub-GHz presets, which lets us manually define how the radio behaves instead of relying on generic defaults. These presets let us specify things like the modulation type, the bitrate or symbol rate, frequency deviation, as well as various other radio parameters. Instead of hoping a preset matches our device, we can describe the signal exactly as the fireplace expects it. And honestly, once you know the values you need, this really isn't that complicated. To make things even easier, there's a great community tool called Flipper Toolbox. The repository describes itself as random scripts and links for generating, creating and modifying Flipper 0 data files, which is exactly what we need here. Inside it, there's a Python script called sub-GHz preset gen.py, which we can generate a valid preset block automatically. All we have to do is give it the parameters we've already measured. So first, I jump back into URH and create a fresh sub-GHz file from one of the known good captures. I name it, save it, and use it as a baseline file we're about to modify. Opening the file in the terminal, we can see the preset section right away, and this is where things were previously going wrong for us. Now I run the Python script from Flipper Toolbox, passing in our known values, including the 20 kHz deviation we measured directly from the original remote. The script outputs a correctly formatted preset block ready to use. I copy that generated preset data and place it straight into our sub-GHz file, replacing the generic preset we were using before. At this point, the radio behavior is much closer to the real remote, but we still have one more problem to fix. The raw pulse timings inside the sub-GHz file are still based on the flipper's original capture rate, which we know is about twice as fast as the fireplace expects. Instead of adjusting dozens of timings by hand, I wrote a small Python script that takes all the raw pulse timings and scales them based on a rate factor. This lets us automatically bring the flipper's timings back in line with the original remote. Once those timings are adjusted, I copy them back into the sub-GHz file, save it and load it onto the flipper. I press the button, the fireplace turns on, and just like that, the flipper is now transmitting a signal that matches the original remote, not just in data, but in timing, deviation, and radio behavior. So why couldn't we capture this signal with the Flipper 0 originally? Well, the flipper itself also uses the CC1101 radio chip, and that chip is not a raw radio frequency recorder. Instead of capturing the actual radio waveform, it demodulates and filters the signal internally and only outputs what it thinks are digital ones and zeros. The problem is that this remote uses very short pulses, around 30 to 50 microseconds. Those pulses are too fast for the CC1101's internal modem, which is designed for structured data streams and not arbitrary pulse timings. By the time the signal passes through automatic gain control, channel filtering, and bit slicing, those short pulses get smoothed, stretched, merged, or dropped entirely. So even though the RF signal exists on the air, the flipper never sees it accurately. It only sees the modem's interpretation of it. Think of it like subtitles instead of a video recording. You only get what the decoder understands and not the raw signal. But then again, I hear you ask, well, why can we transmit the signal even though it can't capture it? Well, when you transmit, the CC1101 doesn't have to analyze or interpret anything. It just turns the radio on and off exactly when you tell it to. A custom.sub file gives the flipper explicit timing instructions. transmit on for 50 microseconds, off for 100 microseconds, repeat. The CC1101 simply replays those timings, even if they're too fast or irregular for its receiver to decode. So while the CC1101 struggles to measure very short pulses on receive because of filtering and decoding, it has no problem generating them on transmit. Receiving requires understanding, while transmitting only requires accuracy. Now that we fully understand the signal, it's time to build something much more permanent. For this project, I'm using ESP32 Room 32, powered with a CC1101 sub-GHz radio module. This will give me full control over the radio parameters like the timing, the deviation and modulation, everything the flipper struggled with earlier. The wiring itself is actually pretty straightforward. The CC1101 runs at 3.3 volts only, so it connects directly to the ESP32's 3.3 volt rail with a common ground. SBI handles all the communication. Chip select goes to GPIO 5, clock goes to GPIO 18, MISO goes to GPIO 19, MOSI goes to GPIO 23. Finally, our GDO 0 connects to GPIO 21, which the library uses for precise timing and signal control. With the electronics sorted, I needed then a clean way to package everything. So I printed a case from Make a World that fits both the ESP32 and the CC1101 nicely. I'll leave a link in the description for the model in case anyone else wants to print it themselves. And now here's a quick build montage. With the hardware built, the final piece is software integration. Using MQTT Auto Discovery, the ESP32 announces itself to Homeassistant automatically. No manual entity creation and no YAML copy paste. As soon as it comes online, Homeassistant discovers the fireplace controller, along with all the buttons and modes I reverse engineered previously from the original remote, like the power, heat levels, flame effects, and everything should just show up. I published the full project on GitHub, including the firmware, configuration, and all of the command definitions for the remote. The repository includes the ESP32 code, CC1101 configuration, MQTT setup, a web interface as well, documentation and everything explaining how it all fits together. If you want to build this yourself, adapt it to a different device, or just dig into details, the link is in the description. And with that, the fireplace is now fully integrated into my smart home. Controlled locally, no cloud, no proprietary apps, and no original remote required. Mission accomplished. If you made it this far, thanks so much for sticking around. If you haven't subscribed, please do, and I'll catch you next time.